Thank you, Bruce. My name is Mark Palmer, and I'm the application engineer supporting Microchip's family of IrDA standard protocol handling devices. Today, we will be giving a brief introduction to the wireless communication using the IrDA standard protocol. The agenda gives you an idea of the topics we will cover. First, we will discuss why to use infrared and what some of the typical applications are. We will then give a high-level look at the IrDA standard system. From this system, we will discuss the IrDA protocol stack, the connection sequence that occurs on the IR interface, and then the host UART interface between the Microchip's protocol handler and the host controller. We will then wrap up with what Microchip offers to support this product family. In a typical embedded system application, the interface to the outside world is a serial cable. The embedded application will have a host controller, an RS-232 line driver, and a DB9 connector, and then the serial cable. Microchip's protocol handler device allows an analogous visualization. Here, the RS-232 line driver is replaced by the MCP21XX protocol handler. The DB9 connector is replaced by the optical transceiver circuitry, and the serial cable is replaced by light. So what are some of the advantages of an IrDA standard interface? First, you have the enhanced mobility, since cables are no longer required. How useful do you think it would be to transfer data between PDAs if you always had to carry your cable around? Would data such as address contacts, photos, programs be transferred as often? Probably not. But since IrDA is a universal standard available on PDAs, notebook PCs, mobile phones, it ensures the interoperability with these many existing devices. With some other wireless technologies, such as RF, they radiate noise, which can cause interaction and interference. But since IR uses light, which is directional, these issues don't occur. This lack of interference means that IR is safe to use in almost any environment, such as planes, hospitals, and this also eases any regulatory approval that you may need to get. Lastly, the cost of the wireless solution can now be implemented near the cost of a wired solution. Some of the common applications where you find IrDA standard ports include PDAs, notebook PCs, or some printers, mobile phones, and pagers. And one that I regularly use is a heart rate monitor watch, which uses RF between the pickup mechanism across your chest to the watch, but you use the IrDA interface to download the exercise data back to the PC. Now we're going to look at an IrDA standard system. Starting on the right, we have the primary device, in this case, a PDA. And on the left block, we have an embedded system, which is a secondary device. The embedded system can be broken into three parts. You have the IR interface with the optical transceiver. In the middle, you have the protocol handler. And on the left side, you have your host controller side, which includes the host UART. Looking at the protocol stack that is implemented in the protocol handler, basically the IrDA protocol stack follows the OSI network model. But the IrDA organization has chosen to implement the structure a little different in appearance. At the bottom of the protocol stack is the physical layer. And this specifies how the data looks like, basically your bit format, and how the bits are going to travel over what type of medium. The IrDA standard basically has three specifications for baud rates. Most devices, including PDAs, are the asynchronous serial IR, which is also commonly referred to as SIR. And SIR supports transmission speeds of 115.2 kbaud. PCs and some printers will implement the 4 megabaud. But to ensure compatibility with SIR, they all start negotiation at 9600 baud. And that's why PCs can talk to PDAs and you can basically do the hot syncs. Okay. Microchip's protocol handler implements the SIR specification. Now we move to the middle area of the protocol stack. Basically, these layers handle the formatting of the message, or you can think of as packet, error correction for the data packet, routing of the data, end-to-end communication control and link management, as well as other communication issues, as well as structuring the information for the application layer of the protocol stack that you'll be using. So now we're at the application layer, and basically the application layer is where the different application protocols can be selected. You can think basically of application protocol as a language, and for two devices to communicate, they're going to have to be using the same protocol or same language. If they're not, then communication will not be successful. So you can see that across on the IrDA they have several types of application protocols. The one that a lot of people think of when people say, oh, I'm just going to send you something, I'm going to use IR and send you something, or beam you something, that's really referred to as IR-OBEX, which stands for IR Object Exchange. In that particular application protocol, the characteristics of the information that's going to be transferred are known. You're going to beam an address contact, you're going to beam a photo or a music file or a program. IRCOM is the IrDA standard for the replacement of your serial communication ports on the PC. And as you know, on those ports, basically all the data comes across asynchronous. You don't know the characteristics of the data that's going to be coming along. The MCP 21.5X and 2140 devices implement IRCOM, and of IRCOM, a portion called the 9-wired Cook service class. Okay. Just remember that Microchip's protocol handlers handle all of this protocol for you. So basically, when you are doing your communication from your host controller to the protocol handler, you're talking to the protocol handlers if you talk to a normal UART, and the Microchip's protocol handler is handling all of that protocol stack for you. Now we're going to look at the connection sequence that occurs on the IR interface. Basically, you can think that there are the three states that the IrDA standard protocol stack could be in. These states are normal disconnect mode, discovery mode, and normal response mode. The first state, normal disconnect mode, is basically when the IrDA devices are searching to see if there's any other device out there that it would like to talk to. When it comes in contact with a device that it would like to talk to, the next state would be discovery. And that's where it determines the characteristics that the two devices can support. Maybe one device has the capability to do an IR baud rate of 115.2K baud, but the other device is limited to 9600 baud. The third state then is normal response mode. After the two devices have discovered each other and formed a link, they move into the normal response mode where data can be transferred back and forth. And this is also where the two devices will maintain the link to ensure that if the link is broken, they don't hang up. Looking more closely at NDM state, the primary device is searching for other devices by sending out XID commands. These XID commands will indicate a time slot. Typically, they will go from 0 to 7, but that is dependent upon the IrDA standard protocol stack that is used. When the secondary device gets in range of the primary, it will respond to one of these XID commands and claim a particular time slot. The secondary device then ignores the remaining XIDs that will be sent by the primary device. After the primary device has completed sending out the entire list of time slots, it will then send out a broadcast ID. None of the primary devices will respond to that broadcast ID. So now we are going into the discovery mode. At this point, the primary device is going to send an SNRM command with particular parameters and a connection address. The secondary device then will respond to this command with a UA response with parameters using the specified connection address. The primary device will then open a channel for IAS queries, which the secondary device will respond to, confirming that channel. At this point, it is now the time for the capabilities of each device to be determined. And these capabilities include the IR baud rate, the data packet size, the turnaround times, and a few others. There's about 7 items that they negotiate. So the primary device will send its capabilities, and the secondary will respond with its capabilities, and the highest common denominator will then be used to optimize system performance. At this point is now the responsibility of the primary device to send an open channel for data. On a PC, this really only occurs after a PC program has attached to the IR port. So for example, if you just have your IR port enabled on a PC and you bring a secondary device in range, you will see on the system tray a little IR icon, if appropriately configured, come up and indicate that a device has been located. But a link will not be established unless a PC program actually opens and connects to that IR port so data can be communicated across. All right. On a PDA, this basically occurs when the PDA wants to transmit its first byte or packet. When that occurs, then the secondary will confirm that the channel is open for data, and when the MCP21-5X or 2140 confirm that the channel is open, it will also drive the appropriate signal low, and that's either the carrier detect or the DSR signal, to indicate that the link is open and available and that data may be transferred. At this point, we move into normal response mode, and this is the state where both data and status information is transferred back and forth. The status information is also the mechanism to verify if a link is still connected. So, as with a wire, you can't really break the link unless you pull it out of one of the connectors. When you're using IR, it's actually could occur that you move the devices so they're no longer pointing at each other, and that would cause the link to break. And if you've seen on your PC, if that occurs, a little message comes up saying, hey, the link is obstructed, please remove the obstruction or we're going to terminate this link. Okay? If the link is blocked for a longer time than the particular timeout, the devices will reset and go back into the NDM state. Whenever communication is completed, the primary device can shut down the link by basically issuing a shutdown link command, and the secondary device will confirm this command, and at that point also both devices would return to the NDM state. Now, looking back at the embedded system, we're going to look now at the interface between the host controller and the protocol handler. In this interface, the CTS signal must be monitored by the host controller. This is so the host controller knows when it can transfer data to the protocol handler. Any data that is transferred while the CTS signal is high is ignored and will be lost. All right? Occasionally, the host controller may also be busy. It may be in a tight loop doing some operation where it cannot be interrupted. In that case, there is the signal, the RTS signal, that can be used by the host controller to tell the protocol handler, don't send me any of the data packets you may have. And the protocol handler will then wait for the host controller to bring the RTS signal back low. If the RTS signal is deasserted for too long, while the data handler has data pending for the host controller, the link will be closed. Now, the 21.5x devices basically window their time. And they window it between either focusing on the host UART side of the interface or on the IR side of the interface. The CTS signal can only be valid during the window where the host protocol, the protocol handler, is operating on the host UART. This window is about 22 milliseconds wide, and the host UART receive buffer is 64 bytes deep. So the host controller can transfer data during this 22 milliseconds up to the maximum of 64 bytes. The table below shows how many bytes can be transferred in 22 milliseconds for a given baud rate. So for the baud rate 19.2 kbaud and below, you're not able to transfer 64 bytes in that 22 millisecond window. You can transfer 42. So you really don't need to, you can just monitor the CTS signal and make sure that you follow that. On the, when you have a host UART interface that is 57.6 kbaud or higher, you're actually able to send data more bytes than the 64 byte limit. So at that point, you will either just need to do a quick counter, sending the bytes out for 64 bytes, as long as you can ensure that the total 64 bytes occurs within that 22 millisecond window. Looking at it in a figure, here's a visualization of the CTS and the received data time window operation. Assuming that the host controller baud rate is 57.6, excuse me, kbaud, and that there is no byte-to-byte spacing and a minimum latency from when the CTS goes low to the start of the data transfer from the host controller, you know that when CTS goes low, that the MCP 21.5x host UART receive buffer is empty. Once 60 bytes have been received, the CTS signal will be driven high. And the reason for this is to indicate to the host controller that use a transmit FIFO on the UART, get ready to stop. And the 21.5x can receive an additional 4 bytes. When the 64 bytes have been received, the data will be processed, formatted, and then transmitted to the primary device. If the host UART baud rate is 19.2, then the received data time window will be closed, which forces the CTS high before the 64 bytes could be received. The data in the host UART receive buffer will be processed, formatted, and then transmitted to the primary device. Any data that is being received when CTS is driven high will not be lost. Now, taking a look at how the MCP 2140 operates, it operates a little differently. It's actually monitoring both the host UART and the IR side interfaces at the same time. So there is no receive data time window. When CTS is low, the host UART receive buffer has space available. So you know that when CTS falls, the entire 29 bytes of the host UART receive buffer are available. CTS will be driven high when 23 bytes are in the host UART receive buffer. Again, this is to give notice to host controllers that use a transmit FIFO on the UART. The data packet size for the 2140, though, is still 64 bytes. So data coming from the primary device would still be able to be in a 64-byte packet. So some of the, here's a visualization of where app notes that we have available to assist you in the development of your system. We have one app note which is for the interface between the MCP 21.5x devices and the host controller. So it really talks about the host UART interface. We have an app note discussing the fundamentals of optical transceivers, and that is app note AN 243. And we have just released onto the website an app note for programming Palm OS devices for embedded IR applications, which discusses the how you program Palms, how you use the serial manager routines, and there's actually a working program. We're also in development of 2 more app notes for programming primary devices, one for the Pocket PC device and one for Windows XP devices. Also in support, we have an MCP 2120-2150 Developers Kit available, and this kit includes 2 MCP 2120 Developers Boards and 1 2150 Developer Board. So in summary, Microchip's IrDA standard protocol handler devices can easily be added to systems currently using serial connections with flow control. This then allows the embedded system interface to the many existing devices with an IR port. A list of some of the available application notes, data sheets, and other reference material is available on the next couple of slides. For a complete list of information, please visit the Infrared Communication Design page on the Microchip website. Thank you.